Hello everyone, this is Srilekha Mitai. Today I'll be speaking about heterogeneous multi-type package design. Hello everyone, this is Srilekha Mitai. Today I will be speaking about heterogeneous multi-type package design. This is presentation for W236 class. Below are the following topics which we will cover today. IC packaging and basics, different packaging techniques, monolithic versus heterogeneous, different heterogeneous options, EMIB, that is embedded multi-die interconnect bridge package, and we also compare EMIB with other options, and also will discuss about example of SIP, that is system in package technology for real-time world. Then we will conclude it. In this slide, we will know more about IC packaging. All the integrated circuits enclosed in a case in order to prevent from physical corrosion damage. This process is called packaging. This is the last step in device fabrication. The package is further taken for the post-silicon testing. And also the process or the steps of packaging must be followed carefully for the better power and performance of the chip and also for the cost-effective solution. Slide is about packaging design considerations. The slide is about packaging design consideration. The three important things which we have to consider about packaging are electrical, mechanical, thermal, and economical. So the first one, let's discuss about the electrical. The electrical characteristics of a signal routes are different for on-chip and off-chip. Off-chip route materials should offer lower resistance and capacitance elements for providing better signal transmissions. This slide is about packaging design consideration. The three important things which we have to consider about packaging are, first one is electrical, and the second one is mechanical, thermal, and the third one is economical. Let's discuss about the first one, electrical. The electrical characteristics of a signal routes are different for on-chip and off-chip. Off-chip route material should offer lower resistance and capacitance elements for providing better signal transmission. And the second one is mechanical thermal. The design should be saved from potential damages and also offer effective heat dissipation from chip. Like thermostat, thermoplastic, or ceramic are examples of materials which have preferred characteristics. And the third one is economical. Careful attention should be paid in choosing the appropriate packaging to make it viable for the production. Considering complexity and heat dissipation of the chip or the process technology. This slide is about packaging design considerations. The three important things which we have to consider while packaging are, the first one is electrical, the second one is mechanical thermal, and the third one is economical. Let's discuss about the first one, electrical. The electrical characteristics of signal routes are different for on-chip and off-chip. Off-chip route material should offer lower resistance and capacitance elements for providing better signal transmission. And the second one is mechanical thermal. The design should be saved from potential damages and also offer effective heat dissipation from chip. Like thermostat, thermoplastic, or ceramic are examples of materials which have the preferred characteristics. And the third one is economical. Careful attention should be paid in choosing the appropriate packaging to make it viable for the production, considering the complexity, heat dissipation of the chip or the process technology. In this slide, let's discuss about the different packaging techniques. The packaging techniques are classified into assembly of the submodules. In this slide, let's discuss about different packaging techniques. The packaging techniques are classified into assembly of the submodules or designs on the die. So let's see monolithic or homogeneous. Several components of a system designs are manufactured on a single die. It is called monolithic or homogeneous. Whereas in heterogeneous, this technique allows discrete components of the system to be on the same package. Slide, let's see about the different packaging techniques. Packaging techniques broadly classified into two based on the assembly of the submodules or the designs of the die. Here, monolithic or homogeneous means several components of a system design are manufactured on a single die. So we can see all the several components on a single die here. Whereas coming to heterogeneous, this technique allows discrete components of the system to be on the same package. So this is a difference between monolithic and heterogeneous. In this slide, let's discuss about different packaging techniques. Packaging techniques are classified into two, based on the assembly of the submodules or the designs on the die. So the monolithic or homogeneous means whereas the several components of a system design are manufactured on a single die. Coming to heterogeneous, where in this slide, let's discuss about different packaging techniques. Packaging techniques are classified into two based on the assembly of the submodules or the designs on the die. Monolithic or homogeneous means here the several components of a system design are manufactured on a single die. Whereas coming to the heterogeneous, these techniques allow different discrete components of the system to be on the same package. Let's talk about traditional monolithic package design. Here, different IPs packaged on same die. As the name indicates, mono means single, lithos means stone. So the package design uses single IC package for the entire system design. And also we can see in the figure where it clearly shows us how the CPU, GPU, IO memory and other IPs are all manufactured on a single package. This slide gives a clear sight of advantages and disadvantages of monolithic circuit packing. That coming to the This slide gives a clear sight of advantages and disadvantages of monolithic circuit packaging. Coming to the advantages, we can see it is more denser and we don't have any external interconnect parasitic effect. And there is also no additional cost of making interconnections. Coming to the disadvantages, it has a poor isolation between components and no flexibility to mix and match IPs from different protocol nodes. And also we can see system on chip and production might have to be delayed in certain cases. Till the other okay. This slide gives a clear sight of advantages and disadvantages of monolithic circuit packaging. Coming to the advantage, we can clearly see it's more denser and no external interconnect parasitic effect and also no additional cost of making interconnections. Whereas coming to the disadvantages, it has poor isolation between components and there is no flexibility to mix and match IPs from different protocol nodes unlike like heterogeneous. And we can also see system on chip and production might have to be delayed in certain cases till all the IDs are showing the better yield, especially on the smaller technology nodes. This slide gives a clear sight of advantages and disadvantages of monolithic circuit packaging. Coming to the advantages, we can clearly see it's more denser and no external interconnect parasitic effect, and also we can see no additional cost of making interconnections. Coming to the disadvantages, it has poor isolation between components and there is no flexibility to mix and match IPs from different protocol nodes. And the third one is system on chip and production might have to be delayed in certain cases till all the IDs are showing the better yield, especially on smaller technology nodes like 10 nanometers. Let's look into the heterogeneous design. As shown in the figure here, different IPs can be packaged onto a same systems. Like consider like die 1 and die 2 are the different IPs and they can be on the same system. And also each IP can independently packed on a different process node. And this is very useful to capture the market. So I would like to say an example here. Whereas Intel recently made a deal with AMD and integrated their GPU using heterogeneous technology to compete in the market. S- Um, Here let's discuss about the heterogeneous design. As shown in the picture clearly, different IPs can be packaged on oh my god. Here let's discuss about heterogeneous design. As shown in the picture clearly, different IPs can be packaged onto a same systems. Suppose consider die 1 and die 2 are the different IPs and they can be packed on a same system. And each IP can be independently packed on a different process nodes too. This is useful for to capture the market. And also here I would like to say an example where Intel recently made a deal with AMD and integrated their GPU using heterogeneous technology to compete in the market. And also we can clearly see how this is a motivation. The Moore's law clearly explain that so according to the Moore's law is the observation that the number of transistors in a dense integrated circuit doubles about every 2 years. So we can clearly see how it is getting more costly, difficult to scale and produce dies without yield issues. So this is a motivation for a heterogeneous design. This slide explains about the heterogeneous design. We can see in the picture clearly how the different IPs can be packed onto a same system. Suppose consider die 1 and die 2 are the different IPs and they can be packed onto a same system. And also each IP can be independently packed on a different process node too. And this is useful for the fast time to market. And we can also see how the Moore's law is a motivation. So Moore's law states that in the observation that the number of transistors in a dense integrated circuit doubles about every 2 years. So we can see how it is getting costly and difficult to scale, produce die without yield issues. So this is a motivation for the heterogeneous design. Here we can see the different types of heterogeneous packaging. The first one is multi-die package and the second one is silicon interposer and the third one is MBIB, that is embedded multi-die interconnect bridge. Let's look into the multi-die package. Here the dies are connected through the substrate package as shown in the figure. So we can see in the figure how this package substrate is connected from die to die. And also coming to the disadvantages for this, it has the poor density of die package in connections. Okay. Let's see the different heterogeneous packaging. The first one is multi-die package, the second one is silicon interposer, and the third one is MBIB, that is embedded multi-die interconnect bridge. Let's look into the multi-die package now. In this method, the dies are connected through the substrate package. As shown in the figure, we can clearly see how the die 1 is connected to the die 2 with the package substrate. And coming to the disadvantages, it has poor density of die package connections and also it has a poor density of die to die interconnect. Let's discuss about the second one, silicon interposer. In this method, the inter-die communications happen through the silicon interposer as shown in below figure. We can clearly see how the die 1 and die 2 is connected with the interposer. And also here all the dies have to be connected with the interposer. And this offers more connection density compared to the multi-die packaging. And it is also expensive due to the larger size interposer and through silicon vias. And as I said earlier, all the connections on the dies have to be made through the interposer. So here we can see higher cost of large interposer plus through silicon vias. And it also has a good density of die interposer connection, good density of die to die connections. Let's discuss about the silicon interposer here. In this method, the inter-die communications happen through the silicon interposer as shown in the figure. Here we can see the die 1 and die 2 are connected with the interposer. Even if there are other dies like die 3, die 4, whatever the dies, all the dies have to be connected with the interposer here. So this offers more connection density compared to the multi-die packaging. And also it is expensive due to the large interposer and through silicon vias. So coming to the advantages and disadvantages, so it has good density of die interposer connection and die to die interconnects. Coming to the disadvantage, it has higher cost of larger interposer through silicon vias too. Let's discuss MBIB, that is Embedded Multi-Die Interconnect Bridge. In this method, small SI bridge are connected from die to die. So we can clearly see how the die 1 is connected to the die 2. So the SI bridges are embedded into, which leads to a tighter interconnect density on the periphery of the die as shown below. So they have smaller than the silicon interposer. So the advantages here are good density. MBIP, that is MBIP, that is Embedded Multi-Die Interconnect Bridge. In this method, small SI bridges are embedded into, which leads to a tighter interconnect density on the periphery of the die as shown below. We can clearly see how the die 1 and die 2 are connected with the silicon bridge. So here they are, if we compare it with the silicon interposers, they are very smaller than those. And coming to the advantages, it has good density of die bridge connections and also die to die interconnects. And the important thing here is it has a low cost of silicon bridges. When we compare to the silicon interposer, it has a high cost. MBIB, that is Embedded Multi-Die Interconnect Bridge. In this method, small SI bridges are embedded into, which leads to the tighter interconnect density on the periphery of the die as shown below. So we can see how the die 1 and die 2 are connected with the silicon bridge. And if we compare with the silicon interposer, these are smaller. And coming to the advantages, they really have a good density of die bridge connections and die to die interconnects. And it is very low cost of small silicon bridges, whereas in the silicon interposers, it is very high cost. MBIP, that is Embedded Multi-Die Interconnect Bridge. Here we can see how the die 1 and die 2 are connected with the silicon bridge. In this method, small silicon bridges are embedded into, which leads to the tighter interconnect density on the periphery of the die as shown below. If we compare this with the silicon interposer, we can clearly say they are smaller than the silicon interposer. And coming to the advantages, it has really good density of die bridge connections and die to die interconnects too. And also we can say it has low cost of small silicon bridges, whereas in the silicon interposers, as it is spread to the entire die, it has high cost. 3D SIP technology for next generation platform uses embedded multi-die interconnect bridge. The figure shown here is Interstratix 10 FPGA chip, which has a discrete modules packed on a single chip using MBIP heterogeneous package technology. We can see here the trans receivers are connected with the MBIP and the DRAM connected with the MBIP. So we can see in all the four directions how they are using the MBIP in the next generation platforms. Here, let's compare the heterogeneous packages, that is MBIP and the silicon interposer. Coming to the MBIP, as we can clearly see in the figure, the MBIP has a small silicon chip which is connected from FPGA die to the die on either side. So this is a silicon which is connected to the either side of. Here let's discuss about the MBIP and the interposer and how they differ. Coming to the MBIP, as seen in the figure, we can say that MBIP has a small silicon chip embedded inside the substrate. MBIP dimensions doesn't limit the number of dies that can be integrated. We can clearly see in the figure number 1 that how the silicon is connected to the die from FPGA on both the sides, and also the silicon chip embedded inside the substrate. Even if you observe here, that is on the silicon interposer, where the interposer silicon has to spread. Here let's discuss about the MBIP and interposer and how they differ from each other. As seen in figure, MBIP has a small SI chip, silicon chip embedded inside the substrate. MBIP dimension Here let's discuss about the embib and the interposer and how do they differ. As seen in the figure, embib has a small silicon chip embedded inside the substrate. Embib dimensions doesn't limit the number of dies that can be integrated. In figure 1, we can see how the silicon is connected from FPGA die to the dies on both the sides. Whereas coming to the silicon interposer, we can observe in the figure 2 the silicon interposer on substrate that extends entire die. Therefore, it also requires more micro bumps using the micro vias. And also we can tell that which limits the scalability, and also this is an expensive technique. Okay. Here let's discuss and compare about the heterogeneous package, and let's compare between mbib and the interposer. As seen in the figure, mbib has a small silicon chip embedded inside the substrate. Mbib dimensions doesn't limit the number of dies that can be integrated. From figure 1, we can clearly observe how the silicon chip embedded inside the substrate. You can observe on both the sides how it is connected with FPGA die to the dies on both the sides. Coming to the silicon interposer on substrate that extends entire die, which limits scalability and also is an expensive technique. It also requires a lot of micro bumps using the micro vias that affect yield and complex manufacturability. So we can clearly compare these two pictures and we can tell how the mbib is cost effective compared to the silicon interposer. Embed. It allows the die IO bumps to be placed as close as possible to the edge of the die. As I have shown in the earlier slide, we can clearly see in that image that there is a short interconnect wires. The short interconnect wires improve the performance due to the lower loads. Whereas coming to the interposers that spread out the entire die. So large number of IO or bumps are deployed to make connectivity, which in turn results in longer interconnect and loading. This finally results in the lower performance. We can clearly observe the difference of this in the earlier image I have shown. MBIP is a two-step process. Here we can see how it is connected from bump to package trace. That is the ball. If you look into the image, the balls below the line to the package trace. The package trace are the thin white lines, and it is the package trace again is connected to the ball. That is the one below the die. So it is a two-step process here. The important parameter like insertion loss to crosstalk ratio, ICR, power supply rejection ratio, and PSR. MBIP is a two-step connective process. We can clearly see in the image how it is connected from bump to the package trace. The bump is the balls which are located in the bottom if you observe in the image, and the package trays are the thin white lines, and the next step is the package trays are connected to the ball that is below the die. And here the important parameters like insertion loss to crosstalk ratio, ICR, power supply rejection ratio, powers are lower. MBIP is a two-step connective process. Here we can observe in the image where it is connected from bump to the package traces. Bump are the balls which are located in the bottom of the image, and the package traces are the thin lines. And the second step is it's connected to the package traces to the balls which are below the die. So from this we can say that it is a two-step process. The important parameters like insertion loss to crosstalk ratio, ICR, and power supply rejection ratio are lower here. The interposer is a four-step connective process. Here we can observe how it is connected bump to through TSV, TSV to bump, and bump to the package traces, which are the thin lines, and also the package traces to the package balls. So Whereas the MBIB is a two-step process and this is a four-step connective process. Here in interposer requires TSV for every user signal leading to manufacture complexity, yield loss, poor signal integrity, IR drop. Coming to interposer, it is a four-step connective process. Here we can observe in the image how the bump to through TSV is connected and TSV to bump, and bump the balls below are to the package traces, the thin lines, and also the package traces to the package balls. So this is a four-step process, whereas MBIB is a two-step. And the silicon interposer requires TSP for every user signal, leading to manufacturing complexity, yield loss, poor signal integrity, and IR drop. Continuing about interposer, TSVs also add series caps and resistance, causing high-speed design challenging. Crosstalks in the interposer routing and coupling between TSVs impact ICR, signal to power rail coupling through TSVs impact PSRR. Continuing the interposers, TSVs also add series of caps and resistance, causing high-speed design challenging. Crosstalks in the interposer routing and coupling between TSVs impact ICR. Signals to power rail coupling through TSVs impact PSRR. PSRR is power supply rejection ratio and TSV is through silicon vias. Let's conclude this. Monolithic packages offer maximum performance and utilization without routing congestion. Utilization bottlenecks. Studies show significant performance degradation incurred connecting components using heterogeneous packaging techniques. Example, if we consider for interposer, it's 1.5 nanoseconds. And next generation platforms such as data centers, capabilities, IoT, terabit networking, optical, 5G, 8K video, demands for a high performance and low power, small form factors demanding innovative packaging solutions, which is where the heterogeneous packaging fits to help in the integration of various dies and foster for capturing the market for economic viabilities. Let's conclude this topic. Monolithic packages offer maximum performance and utilization without routing congestion, utilization bottlenecks. Studies show significant performance degradation incurred connecting components using heterogeneous packaging techniques. For example, if we consider interposer, it's 1.5 nanoseconds. Next generation platforms, example data centers, capabilities, IO, terabit networking, they demand for a high performance, low power, small form factors, demanding innovative packaging solutions, which is where the heterogeneous packaging fits to help in the integration of various dies and faster time for marketing for economic viability. Thank you.